In this problem, an air pack of mass m1 is tied to a string and allowed to revolve in a circle of radius r on a frictionless horizontal table. The other end of the string passes through a hole in the center of the table, and a counterweight of mass m2 is tied to it, as you can see in the figure in here. So the suspended object, which is m2, remains in equilibrium, while the puck of mass m1 on the tabletop revolves. What is the tension in the string, the radial force acting on the puck, and the speed of the puck? So let's start with the first question, which is the tension in the string. So actually in the system, we have two objects which are connected to a string. So we can access the tension either by looking at M2 or M1. So for this reason, let's just draw all the forces, so the free body diagram for each object. So let's start by M1. So what are the forces acting on M1? They are the gravitational force. So this is the force exerted by the Earth on this object M1. It's M1G. Then we have the normal force, which is the force exerted by the table on M1, because M1 is sitting on this table. So this is the normal, I'll just call it N. And we have as well the tension in the string. So this is the force exerted by the string on the puck. And let's just call it T1, because it's applied on M1. So these are the three forces acting on the puck M1. That's all. Let's have a look at M2. So at M2, we have again the gravitational force, which is given by M2G. And we have the tension in the string as well, which is the force exerted by the string on the counterweight M2, and let's call it T2. Right? Now, if you want to access a given force, the best way would be to apply Newton's second law on one of the pucks or one of the objects. So actually, it's easier to apply it on, in this case, on the counterweight M2, because we know that M2, it remains in equilibrium, so it's not moving. That means that in part A, if we apply Newton's second law on M2, then we end up with plus T2. So let's take this to be the x-axis. Let's just take y-axis, and the x-axis to be upwards and rightward. So we end up with plus T2 minus M2G is equal to 0, because the object is in equilibrium. And so therefore we can immediately deduce that T2 is equal to M2 times G. So we know it's the value, or M2 is given. We don't have the value, but it's given in the text. So T2 is equal to Mg. Now, since we have the same string that connects both of these objects, we know that the magnitude of the tension T1 is equal to the magnitude of T2 is equal to T. And so from here, we can deduce that the tension in the string T, it has the magnitude, or it has the value equal to M2 times G. And this is the answer. If you go on with the part 2, you have to determine the radial force acting on the puck. So here's the puck, and we have to know this puck is revolving. So it's actually moving on a circular path of radius r. And since it's moving on a circle, that we know definitely that there should be a radial acceleration, and therefore there should be a radial force. So let's apply Newton's second law on this puck M1 and then see what is this radial force. If we apply Newton's second law on the puck M1, we end up with, so of course, again, sum of external forces, or F net, is equal to M1 times A1, right? So let's start with, so we end up with N plus M1G plus T1 is equal to M1 A1. Now, the point is that we're looking for the radial force. So this is why you have to take the projection of this Newton's second law onto the radial direction. So here is the radial direction. The radial direction is the direction which okay, I mean, whether you take the radial in this sense, where actually it's pointing outwards, so towards the external side of the circle, or if you take the centripetal acceleration, doesn't matter, both are correct. So if we project this Newton's second law onto this radial onto this radial direction, so M1G and N1 they have both zero projection because they are both perpendicular to this direction. We only are left with the projection of T1 onto the radial direction, and so we end up with minus T1 because it's opposite in direction with respect to the direction of this axis. It's equal to minus M1 A1R, where A1R is the radial acceleration of the puck of mass M1. Because also the radial acceleration of the puck is expected to be towards the center of the circle, as you can see in here. We know from the lecture that the radial direction all the time points towards the center of the circle, which is the same as centripetal acceleration. And so we end up with those minus sign cancel out. And so we end up with the tension T equals to M1 A1R. And so from here, we can deduce that the force that is responsible for the radial acceleration is nothing else than the tension in the string. Finally, you have to determine the speed of the puck. So if you know what is the expression for A1R, then it's very easy to guess what is the speed of the puck. So actually, we know that T is equal to M1 times A1R, and we know that the radial acceleration has the expressions equal to V squared over R. So let's replace each of these variables by its expression. We know that T is equal to M2 times G. So M2 times G is equal to M1 times A1R, so it's the radial acceleration of the first puck is equal to V1 squared divided by R, where R is the radius along which the puck is moving. And so from here we can deduce that V1 squared is equal to, so V1 squared is equal to M2GR divided by M1. So it's M2 over M1 times G times R. And if we're looking for V1, then you have to take the square root of this expression. And so that's it for this exercise. You of course have the solution up there below the exercise.